Okay, let us proceed now for the processes of ideal gas. First, we have the isometric process. Isometric process, which is also known as isochoric or isovolumetric. Process. Okay. Under the isometric or isochoric or isovolumic process, this one is a reversible constant volume process. A constant volume process, may be reversible or irreversible process. And always remember that only the isometric process has a reversible or irreversible process. The rest is under the reversible process. Now, under the PV diagram, that is pressure volume, since this one under the isometric process, constant volume, which means your V1 is the same as V2. Okay. Even the pressure decreases or increases, the volume remains constant. Okay, let this one as your P2, and then this one is your P1. Okay, if you notice, even the pressure decreases or increases, the volume remain constant. Therefore, we have from 1 to 2. Okay. Then under the TS diagram, that is temperature and entropy plane diagram. Okay, we have TS plane. As the temperature increases, the entropy also increases. This one is your 1 and 2. This one is your S1. This is your S2. Okay, again, under the pressure volume diagram, as the pressure increases or decreases, the volume remains constant. While under the TS diagram, as the temperature increases, the entropy also increases. Your S here is entropy, T is the absolute temperature, P is the pressure, V is the volume. Now, we have the relationship between the pressure and temperature. Okay, for letter A formula, we have T2 over T1 is equal to P2 over P1. Okay, the temperature here is absolute temperature and the pressure here is the absolute pressure. Therefore, if the given is a pressure gauge, you have to convert it into absolute pressure by adding the constant value of the atmospheric pressure. While if the given temperature is under degrees Celsius or degree Fahrenheit, you have to convert it into absolute temperature. Just add 460 to get degree Rankine for degree Fahrenheit and add 273 for plus the degree Celsius that would be in Kelvin. Letter B. We have the non-flow work, where the non-flow work is equal to the integral of P dV with the limits from 1 to 2. Therefore, that is equal to P V2 minus V1. Since the volume in isometric process is 0, therefore the non-flow work is equal to 0. Letter C. Now, the change of internal energy, delta U is equal to mCV T2 minus T1, where M is the mass, CV is the constant volume specific heat, T2 final temperature, absolute temperature again. Again, delta U is the change in internal energy. Letter D, formula for the heat transferred. The heat transferred is equal to mCV T2 minus T1. Okay. If you notice the same formula for delta U and heat under the isometric process. Letter E, the change in enthalpy, which is equal to mCp T2 minus T1. Again, your CP is under CP is constant pressure specific heat. Letter F, formula. Okay, we have the change of entropy where delta S is equal to mCv ln T2 over T1. Okay, where M is the mass, mCv ln, CV is the constant volume specific heat, then ln T2 over T1. Again, if the formula is capital T, therefore that is absolute temperature. Okay. Now for the reversible steady flow constant, reversible steady flow constant volume. This one is under the reversible. Okay. The formula is V times P1 minus P2. Volume, absolute pressure. Okay. Letter H for the irreversible. Letter H for the irreversible non-flow constant. Irreversible non-flow constant volume. Then heat is equal to delta U plus the non-flow work. Okay. Okay. Example. Number a gas at 15 psig and 45 degrees Fahrenheit is held in a rigid sealed tank. The gas is heated to 550 degrees Fahrenheit, at which point the density is measured to be 0.1 pound mass per cubic feet. Okay. System. Okay. Gas inside a rigid sealed tank. Sealed tank. Okay, given state, we have your P1 is equal to 15 PSIG. Since this one is under the pressure gauge, add 14.7, which is the atmospheric pressure. Then